In this video here, we're going to take a look at exam revision for methods in differential equations. So for this video here then, all we're going to do is take a look at 2 exam style questions for methods in differential equations. And as you can see here then, this will cover the following topics. So we have first order differential equations. We also have second order homogeneous and non-homogeneous differential equations. And then finally here to finish with, we have boundary conditions. So as always then, what I'd recommend here is that you pause the video and have a go at the questions as they appear, and then just double check that your solution matches what we get on the screen. So that should give us everything that we need here to get started. Let's just begin now with question 1. So let's just get started here then with question 1. So as we can see then for question 1 here, part A, what we want to do then is find the general solution to this differential equation here. Now nice and straightforward then, because all I need to do here to solve this differential equation then is just separate the variables, right? We don't need an integrating factor, nothing like that. All we need to do then is just separate the variables. So on the left hand side here, we want anything in terms of y, and on the right hand side here then anything in terms of x. So what I'm going to get here is 1 over y dy on the left hand side, and then on the right hand side here, what would we get then? So I'm simply going to get sin x dx, okay? So we get sin x dx there, okay? And at this point here then, once we now separate the variables, we can now just integrate both sides. So on the left-hand side here, we have the integral then of 1 over y dy is equal to the integral here of sin x with respect to x, okay? And for these integrals here then, this should be nice and straightforward. So on the left-hand side here, this is ln y, like so, is equal to, so the integral here of sin x with respect to x is simply cos x, okay? So we get cos x, and don't forget here, our constant of integration plus c there. And now what we want here then is just y, right? We want the general solution then. So what I'm going to do here is just take e to the power then of ln of y here on the left-hand side, and also do the same then with the right-hand side. So on the right-hand side here, we get e to the power then of cos x plus c, okay? So e to the power then of ln y here, well, e and ln are just the inverse of each other, so they just cancel and just get left with y then. So y here is equal to e to the power of cos x plus c, okay? And at this point here, we could just say that this is our general solution, or alternatively, what we can also do here is just rewrite our general solution ever so slightly. So what I can also do here then is write this as y is equal to, so e to the power then of cos x plus c, this is just the same here as e to the c times e to the cos x, and e to the c here is just a constant, right? We get e to the c times e to the cos x, like so, and e to the c here is just a constant. So if a is equal to e to the c, in that case here, y is equal to ae to the power then of cos x, okay? Any of these here are absolutely fine for our general solution. I'm going to put it into this form here because we might find that useful for part B, okay? So there we have it then. That gives us the solution to part A. And now for part B then, all we want to do here is find the particular solution which satisfies the condition then that y is equal to 2e when x is equal to 0. Okay, so let's just make a note here then. So y is equal to 2e when x equals 0. Okay. Well, in that case, then what do we get here? So if y is equal to 2e, then what I've got here is 2e is equal to, so you can use any of these forms here. Let's just start with the first form, just so you can see what's going to happen. So I get e to the power then of cos 0, because x is equal to 0 here. So e to the cos 0 plus c. Okay. Now cos 0 is just 1. So what I've got here is 2e is equal to e to the power of c plus 1. like so there. Okay. And again, what we can do here, right, is just use the basic laws of indices here. So 2e is equal to e to the c times e, like so. And what we can do here then is just divide both sides by e, right? So in that case then, e to the c here is equal to 2. Okay? So in that case then, if e to the c is equal to 2 here, if I go back to this general solution here then, well, what I can see here is my particular solution, that's y, is equal to e to the c times e to the cosh x. Now, e to the c then, as we've just deduced here, is equal to 2. Okay? So in that case then, our particular solution here is 2e to the cosh x there. Okay? And there we have it. So this here then is our particular solution, which satisfies the condition then that y is equal to 2e when x is equal to 0. Okay? And again, just as a final note here, any of these are absolutely fine here for your general solution then, or part A. Okay, so let me just make a note here. So general solution. Like I said, any of those is absolutely fine. So tick, tick, and tick there. And this here then, this is our particular solution. Again, let's just make a note here. This is the particular solution there. Okay. And there we have it then. So hopefully nice and straightforward. That gives us the solution here to question 1. So to finish with here then, let's just have a go now at the very last question, question 2. Now question 2 here is certainly more challenging than the previous question, as we can see straight away, right? You just want to find the complementary function for the following differential equation. What we have here then is a second order non-homogeneous differential equation. Okay. So for part A then, let's just start in the top right corner up here. So the first thing that we require here then is the auxiliary equation. So for the auxiliary equation here, that will be given as follows. So what I get here then is m squared plus 2m minus 3 is equal to 0. We've got m squared plus 2m there minus 3 is equal to 0. Okay. So what we want to check here then is whether this factorizes, right? We're looking to solve here. Does this factorize? So in this case here, it does indeed factorize. So what I get here then is m plus 3 and m minus 1. Okay. And this is equal to 0. And what we obtain here then is two solutions for m, right? I obtain that m is equal to minus 3 and that m here is equal to 1. Okay. And in that case then, we can now just state the complementary function here. So the complementary function c dot f is, so this is y is equal to, so I get a e to the minus 3x, like so, plus b e to the power then of x here. Okay, it would just be 1x, but we don't need to write the 1, right? So be to the x there. Okay. So there we have it then. That gives us the solution to part A. That is just the complementary function there. Now for part B then, it says hence find a suitable particular integral and write down the general solution to the differential equation. So don't forget here then that the general solution, so the general solution here is simply the sum here then of our complementary function, c dot f, and our particular integral, okay, p dot I there. So as part B suggests here, we do need to find a suitable particular integral, okay? And this is where things start to get difficult here with these types of questions, right? Finding the particular integral can sometimes be a little bit challenging, okay? Now, when I look at f of x here, okay, when I look at f of x here, then I've got p plus qx plus rx squared So P plus QX plus R x squared. Okay. So what we need to do here then is try. So we're going to try here then for our particular integral y is equal to lambda plus mu x plus nu x squared here. Okay, like so. So this funny looking v here, or u, whatever you want to kind of call it. This is the Greek letter nu here, just in case you're not familiar with this. So, like we said, right, we want to try a particular integral of this form. Okay, so let's make a note again here underneath. So we're going to try then this particular integral. So y is equal to lambda plus mu x plus nu x squared, like so. So what we require here then is dy by dx, right? So we need dy by dx here, which in this case would simply give us mu plus 2 nu x there. So mu plus 2 nu x there, like so. And we also need here the second derivative, okay? So for the second derivative here then, what do we get here? So I simply get here 2 nu there. Okay. So what we're now going to do here is take the first derivative, dy by dx, and also the second derivative here, and substitute those into this equation here, the original differential equation, right? Let's just call that equation 1. Okay. So what I get here then is 2 nu. We get 2 nu plus 2 lots of dy by dx here, so that's 2 lots of this. 2 lots of mu plus 2 nu x there. I've got minus 3y, so y is this here. So minus 3 lots of lambda plus mu x plus nu x squared, like so. And all of this here then is equal to the right-hand side, right? So x squared plus 2x plus 2x there, and then finally plus 1 here, okay? So let's just take our time here, right? We don't want to make any silly mistakes as we go. So let's just start then by expanding on the left-hand side and simplifying if we can. We've got 2 nu there. I've then got 2 times mu here, so that's 2 mu. 2 times 2 nu x here. So that's 4 nu x there, like so. Minus 3 times lambda, minus 3 lambda, minus 3 times mu x here. That's minus 3 mu x. And then finally, minus 3 times nu x squared here. You get minus 3 nu x squared there. Okay, and again, this here is equal to x squared plus 2x plus 1. Okay. So at this point here then, all we now need to do here is compare coefficients. So let's just begin here then by comparing coefficients of x squared. So I just make a note here. So comparing, I'm just going to say comparing x squared here. What I mean then is the coefficients of x squared. So in that case then, comparing coefficients here of x squared, I get minus 3 nu. So minus 3 nu here is equal to 1. Okay, the coefficient here of x squared on the right-hand side is simply 1. And then at this point here, right, let's just solve for nu. As we can see, then nu is equal to minus 1 over 3 there. Okay. Now let's move on then. So at this point here, what we now want to do is compare coefficients for x here. So our terms involving x. So we do need to just be slightly careful here. We're going to just make a note here that we're comparing x. Okay. What I probably should have done here as well is just group the x terms together. But as we can see, right, it's just the 2 terms here. So I've got 4 nu x and minus 3 mu x here. Okay, so comparing coefficients, so we've got 4 nu minus 3 mu is equal to 2. Okay. Well, we know then that nu here is minus 1 over 3. So we just do 4 times nu here, which is minus 1 over 3. And then we just need to solve for mu here. Okay, so if you solve this here, what you should get then is minus 3 mu. Minus 3 mu is equal to 10. Minus 3 mu is equal to 10 over 3. There we go. And then just divide by minus 3 here. And what we get then is mu is equal to minus 10 over 9 there, right? So minus 10 over 9. And then what else do we need here? I need my constant term, right? So comparing constants then. So comparing constants here. Like you can see, these questions really are quite lengthy. So comparing constants here. So we've got 2 nu, 2 mu, and minus 3 lambda. So 2 nu, 2 mu, and then also minus 3 lambda, like so, is equal to 1. Okay, like so. And again, at this point here, right, all we want to do then is solve for lambda here. So we just rearrange here, 3 lambda is equal to 2 lots of minus 1 over 3. 2 lots of minus 1 over 3. 2 lots of minus 10 over 9. 2 lots of minus 10 over 9. And then finally, minus 1, right? So minus 1 there. And if we just solve for lambda here, I won't go through the full working. This should hopefully be pretty straightforward at this point. What you should get here then for lambda is minus 35 over 27. Okay. And in that case then, what that means here is our particular integral, p dot I here, is y is equal to, so lambda is minus 35 over 27. So minus 35 over 27 plus mu x here, where mu is minus 10 over 9. Minus 10 over 9x there. And then finally here, for nu then, what did we get here? Nu is equal to minus 1 over 3. So minus 1 over 3, minus 1 over 3 x squared there. Okay. So that's our particular integral here. And then at this point, we're pretty much complete, right? Don't forget here then that the general solution is simply the sum of the complementary function and the particular integral. Okay. And to finish with then, let me just quickly do that in a different color here. Let's just do it we'll do it in green here to finish with. So the general solution here is given as, so this is y is equal to, so I've got the complementary function here, so that's ae, so minus 3x, plus be to the x there, minus 35 over 27, minus 10 over 9x, and then finally minus 1 over 3 x squared here. Okay, there we have it then. So this here, this is our general solution, and that would give us the solution there to part B. So as you can see here, right, these questions are certainly not easy, and especially right when f of x here is something a little bit more complicated, such as this here, x squared plus 2x plus 1. It does make life a little bit more difficult than obtaining the particular integral. Okay. But there we have it then. So that gives the solution here to the very last question for this video here. And that brings us to the end then of this video here on exam revision for methods in differential equations.